know that as we grow, the hurdles will be more. Each time we are washed away, we bounce back to the shore. We know we lead the way, keeping odds at bay. See the sunrise tomorrow, inspire the world to follow.
Okay, I am Sumanto Kundu, Assistant Professor of Department of Electrical Engineering, Narula Institute of Technology under GIS Group Educational Initiatives. So, in our last class of electric drives, we have started module number 1, and the topic we have discussed last class is dynamics of electric drive, and today also we will continue with the same topic, that is dynamics of electric drive of the curriculum electric drive E701. And regarding this, we are going to cover the equivalent values of drive parameter for rotational load, for translation load, and then we will discuss about different characteristics and nature of different load which is connected to the shaft of the motor, and we will discuss steady state stability and transient stability. So these are the topics we are going to cover in our today's class. Okay. So let's start lecture number 4. So before we developed the concept of equivalent values of drive parameters, we should know what is our course outcome and objective. So this is my course outcome and objective. To become familiar with dynamics of electric drive, students will be able to select electric motors for a particular drive based on characteristics. So let's start equivalent values of drive parameter, and in this context we will discuss load with rotational motion, load with translation motion, and third we will determine measurement of moment of inertia. Okay. Now, so equivalent values of drive parameter. Okay. So different parts of load may be coupled through different mechanism. Motor generally drives a load, we have seen, and that motor and load are connected through some transmission system, and that transmission system can be V-belt, crankshaft, gear, etc. Now these parts have different speed and different types of motion. As we have mentioned earlier, it can be rotational, it can be translation, or it can be combination of both of these two, that is rotational and translational. Okay. So first we are going to discuss load with rotational motion. So first we are going to discuss load with rotational motion. So here is the schematics of the load which is connected with the motor's shaft, and here two loads are connected as we seen in the figure. One is connected directly to the shaft of the motor and other through the gear, and that gear has a teeth of N and N1. Okay. So, this J0 is the moment of inertia of the motor and load directly coupled to the shaft. Omega m is the speed of the motor in rad per second. This T10 is, or TL0, whatever you can assume it. So, it is the torque of directly coupled load. So, this load is directly coupled and this load is connected through gear. Okay. Similarly, these are the parameters of the load which is connected through gear. Okay. So, J1 is the moment of inertia of load coupled through gear. Similarly, speed is a suffix 1 is appeared. Similarly, in case of torque, there is one suffix 1 is appeared. So, for directly coupled load, it is 0, denoted by 0 or not, and for the load which is connected through gear is represented by, parameters are represented by this suffix 1. So, J1, omega m1 and TL1 are the respectively the motor inertia, speed and the torque of the load coupled through gear. Okay. Now we know this is basically a concept of mechanical engineering, that we can define A1 as gear ratio. We can define A1 as gear ratio. Okay. So, A1 is my gear ratio, which is equals to angular velocity of output gear by angular velocity of input gear. So, this is my gear ratio. So, if we see what is my angular velocity of the output gear. So, this is my output gear and this is my input one. So, it is omega m1 by omega m equals to n by n1, that is my ratio of the gear teeth, similar to the transformation ratio. We can assume this as A1, and this A1 is known as gear tooth ratio, or this is also known as speed ratio. Okay. Now, in our next class we have seen that when we have deduced the basic torque equation, that is TE equals to TL, that is the load torque, plus J d omega m by dt, that is ddt of omega m, and which we have denoted as J ddt of omega m, and this is we denoted as dynamic torque. And this dynamic torque is basically the thing which is the additional torque is provided so that motor overcome the initial inertia of the shaft, and the energy associate with this dynamic torque stored in the form of kinetic energy. So, whatever energy is with this torque, because we know the torque into angular speed is my power. So, the power related to this torque is nothing but the kinetic energy, and my motto is to replace this system with the equivalent values. So, let us take that whatever system we will develop, that system has a equivalent inertia J. So, if the losses in the transmission are neglected, the kinetic energy due to equivalent inertia must be same as kinetic energy of various moving part. So, if we see in the figure, what are my moving part? So, these are my two moving part. One is connected with gear and with another load is connected directly to the shaft. So, what is the kinetic energy of this plus what is the kinetic energy of this? That should be equivalent to the equivalent system kinetic energy. Okay. So, for this the kinetic energy is half J0 omega m square. So, half J0 omega m square, and for this half J1 omega m1 square. So, it is half J1 omega m square. So, I am trying to develop the equivalent things, that is similar, we can say logically similar to the transformer equivalent circuit referred to the primary side or referred to the secondary side. Just you can take the logic, only the logic thing. Okay. So, what happened? So, the losses, transmission losses are neglected. So, we can write down the total kinetic energy of the moving part is equal to the kinetic energy of that equivalent system, that is half J omega m square equals to half J0 omega m square plus half J1 omega m square. So, from here we will get J equals to J0 A1 square J1. How? Because this half omega m square will cancel. Okay. So, we will divided this equation with half omega m square. So, if we divide, it is my half, sorry, it is my half J omega m square equals to half J0 omega m square plus half J1 omega m1 square. So, if we divided this with half omega m square, this equation, so J equals to half omega m square will cancel each other. So, J0 and half will cancel each other. So, J1 into omega m1 by omega m whole square, and this is nothing but my a1 square. So, J equals to J0 plus J1 a1 square. Okay. So, this is my equivalent moment of inertia, J equals to J0 a1 square J1. Similarly, one thing we should keep in our mind, that power at the motor and load must be the same. Okay. Now, if transmission efficiency of the gear is taken as eta 1, this efficiency is eta 1. So, what is my input power? My total input power is input torque into angular speed, that is my T1 omega m. This is my, this TL or T1 is my the equivalent torque, okay, which is referred to the total, referred to the this motor side. Okay. So, here the speed is omega m. So, T1 omega m equals to, so for this load it is T1 naught omega m, and for this is TL1 omega m1. So, this is TL0 or 10, or this is T11 or L1, whatever you can take. So, this is my power. So, T1 omega m plus TL0 omega m plus TL1 omega m1. Now, this T1 omega ml, this T1 omega ml is my input, output. So, what is my efficiency? Now efficiency equals to output by input. So my efficiency equals to, my efficiency equals to output by input. So what is my input? It is output by efficiency. So what is my efficiency? Torque, that is TL1. What is my speed? Omega m1 by eta. So this is the input power of the load which is connected through the gear. Okay. So this is the gear load, and this is for the load directly connected to the shaft. So this should be equal to the motor power, that is omega m T L or T1. So again we can divide it, this equation, by omega m. So it will become T1 or TL equals to TL0 plus, now omega m1 by omega m, again A1. So this will be A1 TL1 by N1. So this is my equivalent torque, and this is my equivalent moment of inertia. Now here with the gear, the load connected is, the number of load connected is 1. So if there is m number of load is connected, suppose if there is m other loads with moment of inertia j1 j2 dot 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 jm connected, and according to the gear ratio is from a1 to m, then this equation will become j equals to j0 plus a1 square j1 plus a2 square j2, and so on up to the number of the loads. And similar thing will happen with this. Similar thing will happen with this. Now here the load, this load is connected through this gear system. Now this load also can be connected through belt driven drive. Now for belt driven drive, the ratio which was gear ratio in case of gear, here it will be A1 equals to, it will be diameter, dia of wheels driven by motor, dia of wheels driven by motor ratio, that is divided by dia of wheels mounted on the load shaft, So for, if it is not connected with gear, if it is a belt driven drive, so in that case the ratio will be dia of the wheel driven by the motors by dia of the wheels mounted to the load shaft. Now quickly we will discuss about load with translation motion. So this is the figure. So this load is directly connected to the shaft, and this load is connected through some system, through some transmission system, and this transmission system is responsible for converting rotational motion into linear motion. Similarly, for two loads, there are two parameters for it, J0 omega m T L0, and for this it is m1 f1 and v1. So J0 omega m T0 are respectively the moment of inertia, speed and torque of the directly coupled load which is connected with the motor shaft directly, and m1 v1 and f1 is the mass, velocity and force of the load coupled through transmission system. So what we have discussed in case of load with rotational motion, same thing is applicable for this, that if the losses is neglected, then kinetic energy due to the equivalent inertia J must be same as the kinetic energy of various parts. So half the equivalent inertia J is, if it is J, then corresponding kinetic energy to this equivalent inertia is half J omega m square, and for this load it is half J0 omega m square. so it is half j0 omega m square, and for this is half mv square, that is half m1 v1 square. This is basic physics, nothing else. So again I will divide it with half omega m square, so we will get this equation j equals to j0 plus m1 within bracket v1 by omega m whole square. Similarly, power at load and motor should be same, what we have discussed in case of load with rotational losses. So again, if the efficiency is eta 1, so T1 omega 1 equals to TL0 omega n, and here the power is force into velocity. So F1 V1 is my output power, so input power we have to divide with efficiency. So what we have done, we have divided this F1 V1 with eta 1, so this is my equivalent torque. Now similar thing, if there are m other loads with translation motion with velocities v1, v2, vm and masses respectively m1, m2, m1, mm, then the equation will be in this equation, that j0 equals to j0 plus m1 v1 by omega m square plus dot 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 up to the number of loads, and same for the torque. Okay, so this is load with the rotational motion and load with translation motion. Now we are going to discuss the moment of inertia. Okay, so we are now going to discuss the moment of inertia. So moment of inertia can be calculated in two ways. One is theoretically, another one is practically. Theoretically we can done if we know the dimension and weight of the various part of the load and motor, and practically we do the retardation test. Now what we do in case of retardation test, we run the motor with slightly higher speed of the rated speed, and then after some time we cut the supply. But due to inertia the drive will continues to run off because of inertia, that is the stored kinetic energy, and then deaccelerate due to rotational losses, rotational mechanical losses. Okay, so we have seen in these things in our machine that there is rotational losses exist in case of motor. Now when the speed will start reducing from a particular value, we will take the reading, the speed value and corresponding the time value. So we will record, we will make a tabular form, the speed versus time before it will become stalled or its speed become 0. So suppose at any speed omega m, the power P consumes is, what is the power at any speed? That is the stored kinetic energy which is supplying the losses, because we know from the conservation of energy, energy cannot be created nor destroyed. So who will supply the losses? This kinetic energy will supply the losses, stored kinetic energy. So that's why this P is nothing but the rate of change of kinetic energy. So what is my kinetic energy? We have seen it is half j omega m square. So P is nothing but the time derivative of half j omega square. So if you do the derivative of this, so P equals to, so P equals to P equals to d dt of half j omega m square. Sorry, this is my j. So what is the derivative? So half will become outside, so d dt of uv. So half j into 2 omega m d omega m dt plus half omega m square d dt of j. Now this J, moment of inertia, is constant for a particular machine, so this term is basically 0. So only this term is remain, that is half J. So this 2 will cancel each other, so this 2 will cancel each other, so J omega m d omega m by dt. So this is my J omega m d omega m by dt. Now from retardation test, d omega m dt at rated speed is obtained. Why? Now first I told that when in retardation test we run the motor in rated speed and then suddenly cut the supply, and then we will take the reading of t versus speed. So easily from there we can determine the ddt of omega m. Now what we will do, we will again connect that system to the supply, run the motor at rated speed, we will calculate or we will determine the rotational mechanical power input to the drive, that way we will measure. So now we know this P, we know omega m, we know d omega m by dt, so we can approximately calculate that P. So this is what thing you just think. Here we have made one assumption that the mechanical power input to the drive is equivalent to this rotational losses. But one thing we should keep in mind, that this is not the case. Okay, so what is my disadvantage of this retardation test? So disadvantages of this retardation test is that rotational mechanical loss and core loss are lumped together. When we have read whether it is 3-phase induction motor or single phase induction motor in the equivalent circuit, we seen that in the equivalent circuit we have represent through a resistance the mechanical power, electrical equivalent of the mechanical power developed through a variable resistance. And in that context we have also discussed this in this equivalent circuit, that rotational mechanical loss or core loss are lumped together. They are the summation. We cannot separate these two, so we cannot get the exact value of rotational loss. So that's why we have told that this mechanical power input is approximately equal to the P. Now so for that for retardation test for DC separately excited motor or synchronous motor, what we do for DC separately excited motor, or synchronous motor, what we do in retardation test, we keep the field circuit on. So what happen? So what will happen? Then we know the armature input power. Okay, and we know, as the field is on, we know the armature I square R loss, copper loss. So from the input power, if we subtract the armature I square loss, we will get the value of core loss. So once we get the value of core loss, we can get the exact value of rotational mechanical loss, because this loss and this core loss are lumped together, and that is denoted by the input mechanical power. But here this part is included, so we cannot get that exact value of rotational losses. So what we do in case of retardation test, for DC separate motor, synchronous motor, we keep the field on, and for wound rotor induction motor, what we do, we keep the stator supply on as well as rotor winding connection open. So what we will get, again we will get the exact value of rotational mechanical losses. So if we determine the mechanical rotational losses, then easily we can determine the moment of inertia. Apart from this, we use a plot through which we can determine the moment of inertia. Okay, so what we do, so what we will do, we will determine that omega m versus t. We know we have first retardation test, we have taken the rating of speed versus time. So if we plot that, if we plot that if we plot t versus omega m, because that reading we have taken. Okay, so that will be nature of kind of rectangular hyperbola. Okay, so this is my omega m versus t. Now what we will do, we will determine the p value easily for different speed, and I will plot that value. So it will be like this, it will be like this. So this is my p versus omega m, because for different omega m we can get the value of p. So now what we will do, for a particular time t1, for a particular value, suppose t1, thus we can easily get the value of speed, we can easily get the value of speed. This is, so this is my omega m1. Now for that particular speed of omega m1, we will again get the power. So are you getting my point? For this particular t1, we will get the value of omega m1. For that omega n1, from here we will get the value of power. Okay, so what we will do, we will plot this, we will plot this. What we will plot? We will plot p versus t curve. Okay, so for a particular t1 we will get the value of speed, and for that particular speed we will get the value of p, and for different value of time, that is t1, t2, t3, we will get the similar value omega m1, omega m2, omega m3, and so on, and corresponding value of p1, p2, p3, and again we will plot that curve. So if we plot that curve, it will be again a similar rectangular hyperbola like this. Now this is the area, this area is my concern, this area is my concern. This area enclosed is nothing but the energy dissipated. This area enclosed, suppose this area enclosed is A, capital A. So A is nothing but energy dissipated during retardation test, energy dissipated during retardation test. So this area is nothing but A equals to my half j omega m square. So easily from using geometry we can get the value of A, we can know the value of corresponding omega m square. So easily perfectly we can determine the value of moment of inertia. So this is how we determine the moment of inertia. Now we are going to discuss different load nature. Okay, so let's start the discussion on different load nature. Okay, so let's discuss different load nature. Okay, now we are going to discuss the components of load torque. Now the load torque has the following three components, that is the torque required doing useful mechanical work, which is the prime component of the load torque, for which actually doing the work for the motor is being operated. Now it may be constant or it can be depends on speed. The second one is frictional torque. You know that it opposes the motion, and loss of torque due to friction is called frictional torque. And the third one is windage torque. The resistance of air results in loss of torque and it's referred to as windage torque. So we can write that load torque TL equals to T capital L plus TF plus TV. Okay, so TL is equals to TL plus TF plus TW. Okay, before that we should know that TL equals to TF plus TW and TL. So TL is here the torque. TL is the torque required to do the useful mechanical work, which is the main component. Then that windage loss, that is denoted by TV, sorry, it is TW, and then TF, which is my frictional torque. Okay, so this is the load torque. Now generally friction and windage loss torque are grouped together. So this TF and TW are lumped together and can be expressed as d omega, where d is the frictional constant. The magnitude of friction torque depends on the speed. So we know from the basic physics knowledge of our 11-12 that the magnitude of friction is depends on speed. Now if we show the variation of friction torque with speed, it will be like this figure. So this is my variation of speed. So this is in positive direction and this one is in negative direction. Now friction at standstill, when there is no movement. So in that condition, that is the static friction is come into the picture. So basically that time when the motor is to be started, the torque developed by the motor must overcome that static friction. So motor has to exceed that friction. Basically it is called friction. Actually this term is called in basic physics, if you recall, it is called friction. It is called friction. So we have to cover that friction when the motor is about to start, right? So we can say the frictional torque is the combination of three parts, that is TC plus TV plus TS. Coulomb friction, viscous friction and static friction or friction. Okay, so this TS is basically 0 in dynamic condition. When the motor is in speed or in motor in running condition, the TS is not in existence. And that Coulomb friction is independent of speed. It is basically constant. So the viscous friction is basically the component of frictional torque, which is dependence with the speed, and it's depend linearly. Y equals to mx equation it will follow. So TV equals to b omega n, where omega n is the speed in rad per second and b the viscous friction. This is all are basically basic physics. So TC is independent of speed, so we can represent it like this constant component. Ts is basically 0 in dynamic condition, and y equals to mx equation is following the TV part. So the TF has, the frictional torque has three component: viscous friction, Coulomb friction, and static friction or striction. And if we combine this, we will get this figure. Okay, so this is my variation of friction torque with speed. Now windage loss is basically the torque required, or windage torque, which basically the torque which is required to overcome the resistance offered by the air. So when motor is running in high speed, there is air resistance come into the picture, and this is basically follow a rectangular hyperbola. TW equals to C omega m square. So if we recall that we have written that TL equals to capital TL plus TF plus TW. Okay, so now we got that, so TL will remain TL, that is the main component, that is the torque required to do the useful mechanical torque. Okay, and this TF is combination of TC Coulomb friction, TV viscous friction, and TS, that is the striction, and then TW windage torque. Okay, now this TS is 0 in dynamic condition, so we will get finally TL plus TC, and TV we have seen the y equals to mx equation, B omega m, and it is changing with the speed, so it is square term will appear, we know from our basic mathematical knowledge. So C omega m square. Now the interesting fact is TC plus B omega m, this term is negligible compared to this this TC plus C omega m square term, TC plus C omega m square term, this is basically negligible in comparison with B omega m, that is the viscous torque or viscous friction, and the TL, that is the useful torque. Okay, so we can neglect this. So ultimately we are getting, if we recall that basic torque equation, that TE equals to TL plus J dt of omega m, dt of omega m. Okay, so this J omega by dt term will remain, and in place of TL we will put this TL plus B omega m. So TL, this is basically T small l, this is capital TL plus B omega m. So this is my final torque equation. Now one thing, there is another torque which is denoted as TE equals to KE theta E is there, which is basically called coupling torque. This is called coupling torque. This is basically coupling torque, and this is due to the torsional elasticity of the shaft coupling, but most of the shaft is perfectly stiff, so this T is basically 0, so we don't consider this, into our equation. So this is basically 0. Okay, so this is all about component of torques. Now we are going to discuss nature and classification of torque. The load torque are classified into two categories. One is active load torque, passive load torque. So as the name suggests, active load torque is the potential to drive motor under equilibrium condition, and passive load torque is the torque which opposes the motion, is called passive torque. Now active torque is basically retain their sign instead of changing the direction of drive location. So this is the most important point. Although we are changing the direction of drive rotation, it will keep remaining its sign. It's going to keep remaining its sign. So sign is unaltered, and this is torque due to gravitational force, tension, compression, and torsion are the example. And passive torque, as you know, it will change its sign with the reversal of the motion. This is basically due to friction, windage, cutting, etc. fall under this category. Now this is a typical torque versus speed characteristics of different loads. Okay, so this first one is T constant, that is we have shown Coulomb friction. So this is the nature of the torque versus speed, and this is again T versus omega m square. So this is my T versus omega m square. So which is my basically seen in case of windage friction. Now the third one is T equals to omega m, y equals to mx, we know. So this is y equals to mx, and this is my T equals to 1 by omega n rectangular hyperbola. So this is basically few nature of load torque. So another thing I must show that that for a tractional load the characteristics is like this. For tractional load, the characteristics is like this. So this is basically somehow this type of, this is the characteristics for tractional load. Now why this kind of characteristics? Because the tractional load torque is to be the function of only speed. Traction means our local train EMU, because we have assumed when the train is running the level is ground, but actually the train has negotiated upward and downward slopes. So consequently torque due to gravity, which varies with position, is also present. Furthermore, when a train takes a turn, the friction force of wheel change substantially. Thus, traction is an example where load torque also depend on position and path follow. So this is the nature, traction, which depends on speed, position, and path. So this is a typical nature of tractional load. Okay, so torque is constant. So this first figure, this is basically a low speed hoist. Torque is constant independent of speed. At low speed, windage torque is negligible. Net torque is mainly due to the gravity, that is constant and independent. Paper mill, where Coulomb friction dominates over the other component. Torque is function of speed, that is T is proportional to omega m square. It has a low starting torque. Example is centrifugal compressor, fans, etc. Now linear characteristics, y equals to mx, torque is proportional to speed. Mixer, stirrer, etc. is the example. And now torque is inversely proportional to the speed. It's most important that lifts, lathes, wet bears, winders, reciprocating rolling mills. This is where lift. So in lift, it's inversely proportional, means the torque is reduced as the speed is increased, and vice versa. As the speed decrease, the torque increase. So that's why in the starting, when it is going to start, it has to move a huge mass. So that is lift, that is the torque is proportional to 1 by omega m. Now we will going to discuss steady state and transient stability. Okay, so transient stability. So transient stability. Now, when transient stability occur? Now, during starting, braking, speed change and speed reversal. So, these are the few occasions when the transient comes into the picture: starting, braking, speed change, speed reversal. Now, we know our basic torque equation is T equals to J d omega m by dt plus useful torque plus p omega m. This equation we have derived just few seconds back. Now, this equation basically evaluate the time taken and energy dissipation in motor during the transient operation. So, this equation determine or evaluate the time taken and the energy dissipation E of the motor during transient operation along with other motor circuit equation. Now, in this equation, this T and TL, these two, if this two is constant or proportional to speed, then it is a first order linear differential equation and we can solve it analytically. We have seen our in basic engineering mathematics. If not, means this T and TL, if it is neither constant nor proportional to speed, then it is a non-linear differential equation, and then we have to use numerical methods. We can use RK method, Rage-Kutte method we can use. Okay. Now, in transient, the final speed is my equilibrium speed. My final speed is my equilibrium speed. Final speed is my equilibrium speed. Okay. Now, theoretically, transient are over in infinite time. So, to die out the transient period, theoretically it's take a infinite long time. But in reality, it is not true. Practically, transient operation is considered to be over when 95% change in speed has taken place. So, it's not infinite time. Just to a change of 95% in speed will give the value of transient time. Now, suppose omega me is my equilibrium speed. Equilibrium speed. And omega m1 is my current speed of drive. Current speed. Then omega me minus omega m1 is my change in speed. This is the change in speed. This is my change in speed. Okay. Now 95% of this is my 0.95 into omega me minus omega m1. We can also assume this as omega m2. Later on we will consider this as omega m2. So, what is the transient period or transient time? Now, the transient time is the change of speed from omega m1 to omega m1 plus 0.95 omega me minus omega m1. So, time taken to change the speed from omega n1 to omega m1 plus 0.95 into omega me minus omega 1 is my transient time, because 95% of speed change is my required. So now using speed torque curve of load, speed versus torque curve of load, and the steady state speed versus torque and speed versus current of motor. So mind it. So this is for load, this is for my motor, and this is in steady state. This is in steady state. Can accurately compute the transient time and energy loss. Okay. So now the question that must arise into our mind, that why calculating, why we are taking steady state. We have told us that steady state omega versus t and omega versus I curve. Now why steady state? Because mechanical time constant of a drive is usually very large to electrical time constant. So mechanical time constant is much greater than of electrical time constant. Okay. So if electric time constant is lesser than the mechanical time constant of a motor, so as a result, or rather as a consequence, electrical transient die out very fast. Okay. Now we know from basic fundamental torque equation of drive that T equals to TL plus J d omega by dt. This equation we have derived. Okay. Now I will solve it. So J d omega m by dt equals to my T minus TL. So from here we will get my dt equals to dt equals to J d omega m by T minus TL. So we will take it a function of speed omega m. So this is basically T omega m minus TL omega m. This is basically motor and load torque are the function of drive speed omega m. So torque is basically the function of drive speed omega m. Okay. So from here we can easily determine T. So T equals to J integration of d omega m by T omega m minus TL omega m. Suppose the speed is changing from omega m1 to omega m2, and omega m2 we have seen just few minutes back, it is the 95% speed change. So the speed will become omega m1 plus 0.95 into omega me minus omega m1. So this is my transient time. This is my transient time. Okay. So this is my transient time. Now you should remember that the torque, which is a function of speed, should be known and are of integral form. That is my T and TL. Okay. That is my T and TL. This is these two, T and TL, which is a function of omega m. So these two must be known and are integral form. Otherwise, we have to implement the graphical method. So what we do in graphical method? We do nothing. We just plot speed versus the reciprocal of acceleration, that is my j by t omega m minus TL omega m. This is basically reciprocal of acceleration. Okay. So this gives, if we draw this, so the curve will become very similar to this. So this is my curve. Okay, and this is basically my equilibrium speed omega m, and this is the speed omega m1, and this is my speed omega m2. Okay, so this area, I am not an artist, but I am trying to do level based. So this area is this shaded area, basically the transient time t. Okay, so this is t, and the energy distribution is nothing but E equals to Ri square dt. Okay, where this is R is the motor winding resistance and I is the current through it. So this E is basically energy dissipated in motor winding during transient period. So now we can easily calculate the transient time, and from there we can calculate the energy dissipation. Now we are discuss about steady state analysis. Okay. So now steady state stability. So before we go into the details, what we have just seen in transient stability, that equilibrium speed is the speed in which motor torque becomes small as load torque, is known as equilibrium speed. So the speed at which motor torque is becomes same as load torque, both will become same, then it is called equilibrium speed. Now when some disturbance appears into the system, so the concept of stability comes into the picture. Now what is that stability is basically? It's basically, stability is the capacity of the system which enables it to develop forces of such a nature as to restore the equilibrium after any small departure therefrom. So if disturbance occur, the equilibrium position shifted. Now what is stability? Now whatever may be the disturbance or whatever may be the perturbation, if disturbance occurs, the point of equilibrium shifted, but some forces will return back to it in that equilibrium position. If it return to that equilibrium position, then the system is stable, otherwise the system is unstable. Okay, so if the changes is slow from equilibrium state, then it is steady state, and we have discussed sudden and first change from the equilibrium state is transient stability. Okay, so we will discuss these two graph. Okay, now if we examine these two graph, this is my motor torque curve and this is my load torque curve. Now the position of speed changes from, suppose this is my omega m1 to this omega m2. Okay, so there is a change of del omega m. So my speed is changes from, suppose, del omega m1 to del omega m2, reduce. So this is my del m, that is omega m1 minus omega m2. Okay, and so speed is reduced. Okay, so if the speed is reduced, now you see that in this particular condition motor torque is in this position, whereas load torque is in this particular position. So in this condition the motor torque is greater than the load torque. So if motor torque is greater than the load torque, what will happen? Motor will accelerate and it will go back to this point of A. Okay, so although disturbance shifted the point from A to some other point, but as motor torque is greater than load torque, so it will restore its operation to A. Now if the speed is increased, suppose now the new speed is somewhere in this position. Okay, somewhere in this position. So in this position, if you see, this is my load torque in this position, and whereas this concept, this is my load torque. So load torque in this position, load torque is greater than motor torque. So if load torque is greater than motor torque, what will happen? The motor will deaccelerate. So motor will return to again this position A. So this is my stable, steady state stable point at A. Okay, now let us examine in this system. Now what happened in this system? The speed is reduced, suppose from this position to this position. Now in this position, if you see, in this position the load torque is higher than the motor torque, because this is my motor torque and this is my load torque. So load torque is higher than motor torque. So what will happen? If load torque is higher than motor torque, so motor will deaccelerate and the point further move to this way. So it will go away from B. Now if speed increase, you check, if speed increase in this condition, suppose the speed is now in this position, increase. So in this position, if you see, load torque is higher, whereas motor torque is higher, whereas load torque is less. So if motor torque is higher and load torque is less, then what will happen? The motor will accelerate. So again it will go further away from B. So B is not the stable operating point. Okay. So similarly, when speed increase, motor torque become greater than load torque. So B is unstable point of equilibrium. So what we have established? We have established that an equilibrium point will be stable when increase in speed causes load torque greater than motor torque. When increase in speed, so in this condition, if you see increase in speed, load torque becoming greater than motor torque. So in that condition, we can say that the stable operation is happening. Okay, so that means in stable operation, d omega m of TL must be greater than d omega m of T. So if this satisfied, then it is a stable operation. Now we can prove this condition. Now we know this basic torque equation, and suppose a small perturbation in speed is given delta m. So torque will also change by delta t. So we have incorporated that thing into our equation. So T plus del T equals to TL plus del TL and omega m plus del omega m. So this equation converted into this when a small perturbation in speed occur, del omega m. So from here we get that d omega m by dt. So if we simplify this, j d omega m by dt plus j d del omega m by dt equals to this torque term with small change. So it will become this equation, okay, where we know all this term we have discussed previously, that j is the moment of inertia, omega m the speed, TL load torque, T is the torque of the motor, and this is the change in the speed torque in motor and load due to the small perturbation. Now from this equation we can say that j d omega m by dt plus TL minus T equals to 0. So I will put this value to this equation, okay. So if I put this value, so the other term will become also 0, that is j d omega m by dt plus del TL minus del T equals to 0. This will become 0, okay. So if we put this value here, so see that this j omega m by dt term, this term and this term, it will become 0. So which is left? Del T, del TL and j d del omega m by dt. So this is my leftover, okay. So j d del omega m by dt plus del TL and minus del T. This is also equals to 0, that is what I have said. So this equals to 0. Now for small perturbation, the speed torque curve of the motor and load can be assumed a straight line. This is my assumption, that speed torque curve is linear one, that is y equals to mx. So if it is y equals to mx, then del T equals to dt d omega m del omega m and del TL equals to dTL by d omega m del omega m, because we are discussing about the speed versus torque curve. So slope must be this dt by d omega n and dTL by d omega n. We know that this is my slope m. This is my slope m, because we are talking about speed versus torque curve. So in speed versus torque curve, the derivative with respect to speed is always my slope. We know from our basic mathematics slope m, and we know y equals to mx. So what is my y torque term? What is my t m? This slope term, that dt by d omega n, and what is my x? X is my corresponding speed. So see, that is what we have done. So for del t, it is dt by d omega m by del omega n, and for del TL, it is dTL by d omega m by del m. So now what we will do, we will put this two value into this equation. So that is what we have done. So if we put this equation and we solve, the solution is like this: del omega m equals to del omega m 0 exponential of this term. So this is the solution of this equation 2.19, okay. So where del m0 is the initial value of the deviation in speed. Now from this equation, now if exponent is greater than 0, this exponent term e to the power some whatever is the term, if it is greater than 0, So the speed deviation will increase with time and system will move away from equilibrium. So it is unstable condition. So it is similar to, it will become like it is going exponentially, it is increasing. Okay, and another one is exponentially decreasing, then it is stable. So this is my stable and this is my unstable. Okay, so now if it is less than 0, so if you put here, you will get that is exponentially decreasing curve, so it is stable system. And if it is 0, so it is insufficient to discuss about the stability. So the exponent will always be negative. The exponent is always be negative, and if it is negative, that means it is less than 0, then only it is stable. So we have proved that what we have first told, that the dTL by d omega n must be greater than dt by d omega n. So we have proved this. So this term has to be negative, and if this is negative, so if you put this equals to 0, so this has to be greater than 0. Unless or until this term is greater than 0, unless or until this term is greater than 0, it is not possible. That is that dt by d omega m by dt by d omega m, this term must be greater than 0. So this term must be greater than 0. Okay, so then only the e to the power something negative will become, then it will decreasing curve. So we can say the system is stable. So this is all about the stability of the system. Okay, this is all about the stability of the system. So let me check whether any topic left or not. So most probably we have covered all our topics in module 1. Okay, so hopefully we have covered all the topic in module 1. So quickly let me check. So quickly let me check. So let me check quickly. Yes, we have done concept, classification, parts and advantage of electric drive, types of load, fundamental torque equation, equivalent value of drive parameter for loads with rotational and translation motion, determination of moment inertia, steady state stability, transient stability, 4-quadrant operation. So we have perfectly completed our module 1. Okay, so we have perfectly complete our module 1. So thank you. This is the references we have used to discuss in this module. Okay, thank you.